So today we're going to be doing 10.5, which has to do with similar solids. So just like similar triangles and proportional relationships, it's the same thing that we're going to be looking at, similarities. So let's start. Review similarity in one dimension analysis. So this is just one part, one dimension means one part. So if two shapes are in proportion, then their corresponding sides are in proportion, have a scale factor of x to y. So say I have a cylinder here, and it's proportional to a smaller cylinder here. Basically what this is saying, if this, we know they're proportional, this has a side of length of 24 and this has a height of 3, then we can just do x to y, 24 to 3, which is 8 to 1. So their scale factor here, scale factor x to y is 8 to 1. And that's true for any corresponding side. Okay? Now let's look at two-dimensional analysis. So if two shapes are similar with their scale factor of x to y, then their areas have a scale factor or ratio of x squared to y squared. So first we looked at just sides and single dimensions, and now we're talking about their area. So they have an area, a scale factor, their areas of x squared to y squared. So let's say I have a rectangle here and it's 5 by 3. Then I have another rectangle here and it's 10 by 6. Okay, that means that this first shape has an area of 5 times 3, which is 15. And this one has a shape of an area of 10 by 6, which is 60. So basically, of x squared to y squared, let's look at 5 to 10, right, is our side. X to y has a ratio of 5 to 10, which is 2 to 1. And now we square it. We square the x, right, because we have a side ratio of 2 to 1, so that the areas will have a ratio of, we'll square these, 4 to 1. So basically this is saying sides have a ratio of x to y, which tells us that areas have a ratio of x squared to y squared. So this is our side ratio, then we square them and we get our area ratio. Okay? Moving on. So let's talk about similarity in three-dimensional analysis. So let's start with congruent solids. So like two-dimensional figures such as triangles and solids can be congruent, all their dimensions will also be identical. So for example, any two spheres with the same radius are congruent. Any two cubes with the same sides of the same length, they'll be congruent. So it doesn't matter if we're in 2 dimensions or 3 dimensions, if we have every aspect, every dimension of a figure or shape to be identical, that means that they're congruent. Okay? So if I have a cube with a side length of 2 and another cube with a side length of 2, obviously they will be congruent. More or less that's what that is saying. So here's an example. We have pyramids A and B, and they're congruent. Pyramid A has a base area of 25 and a volume of 75. Find the height of pyramid B. So we know that they're congruent, so we know that the height of A will be the same as the height of B. So let's find the height of A. Volume equals 1/3 base area times height. We know that the volume is 75, which is 1/3 times the base area, which they said was 25, times the height, which is what we're solving for. So multiply by 3 on both sides, and we get 225 is equal to 25 times the height. Divide by 25 on both sides, and we get a height of 9. So this is just us working backwards, using information about A, and we found that the height of A is 9, which means the height of B is also 9, because they are congruent. Okay, similar solids. So solids can also be similar, just like shapes can. So any two spheres or two cubes will be similar once they have only one linear measurement. So either the radius or the length of a side. So if they have one measurement, and it's proportional, that's basically what it's saying. So other shapes such as prism and cylinders must have multiple lengths that have the same proportions shapes in order to be similar. So what this is saying is, if we're talking about two spheres or two cubes, so remember, you know how when we're calculating dimensions of a sphere, all we have to know is the radius. And when we're calculating volume or surface area of a cube, all we have to know is the side length. There's only one, so which basically means that any sphere is going to be similar to any other sphere, and same with a cube. It doesn't matter what the value of the side or the radius is, we know that they will be congruent. I mean, similar. But when we're talking about prisms and cylinders and other figures that we have a base and a height and a length and more than one value or length, they have to be proportional in order for the shape to be similar. So this is what it's saying here. This is our similar solids theorem, which we discussed briefly earlier. We said that, remember, side 1 and side 2 is equal to x2 and y2 for the surface area. Now the same goes for volume, we're just saying that it's cubed. So this states, if two solids are similar with a scale factor of x to y, then the surface areas have a scale factor of x squared to y squared, and their volumes x cubed to y cubed. Okay? We'll do an example of that. Alright, so this example says that the volume of the red pyramid is 5 meters cubed. The scale factor of the blue pyramid to the red pyramid is 3:1. Find the volume of the blue pyramid. So it says the scale factor of blue to red is 3:1. So write 3:1. And it says find the volume of the blue, and we know the volume of the red. So volume equals, we'll call it x. Okay? So we want to know what x is. We want to know what the volume of, and we know that the volume of the red is blue, right? Because this is blue to red, and this is blue to red. So our blue, I'll put in blue here. Now remember, we have to cube our scale factor of the pyramid to get the scale factor of the volumes. Okay, so we have to cube what's on the left to get our volumes on the right. So 3 cubed is 27 to 1, and to x to 5 for the volume. So now all we have to do is solve for x. We get 27 times 5 is equal to x when I cross multiply. So x is equal to 135 meters cubed. Okay, so that's all you're going to have to do is set up a proportion, and you're going to have to be careful. And if it's talking about volume, you'll be cubing. If it's talking about surface area, you'll be squaring. Just make sure that you're squaring the scale factor of the pyramids and not the volume section or the surface area section. You're squaring the right side, okay? The correct side. Okay, let's look at this one. It says find the scale factor of the solid below. So we have the scale factor of the volumes, right? Because we know that x to y is going to give us 729 to 64 if they're proportional. But remember, we have to square the scale factor of the actual solids. We're not squaring the volume, okay? So that tells us that the cubed root of 729 will give us 9, and the cubed root of 64 will give us 4, okay? So all we have to do is 9 over 4, and we get a scale factor of 225 to 1. My advice here is to just be careful and make sure that you're taking your time and making sure that you're cubing or squaring the correct thing. Okay, so this example is a little different. It's talking about comparing densities. Okay, so this says, which sphere has a greater density? The mass of the lead sphere is 10,200 grams, and the mass of the uranium sphere is 5,094 grams. It says, hint that density is mass to volume. Okay, right off the bat, we know that we're using spheres. Automatically, they're proportional. Remember, cubes and spheres are all proportional. Okay, so let's see what their scale factor is. So we have 4 to 3, right? So, 4 to 6, sorry. So 6 to 4, but we're going to talk about volume because it says the density is mass to volume, so we have to find what the volume is, so we have to cube these. And we get a scale factor for the volume to be 216 over 64, which is 27 to 8. Okay, so it end up being volume ratio, and that is 3.375 to 1. Okay, because we want it down to a unit rate or a ratio. All right, so first thing you have to realize is that we had to find the volume, right? Because it didn't give us the volume, but that was easy. All we had to do was cube it. What we had as our original ratio to find the volume. Because remember, for volume, x to y is equal to x cubed to y cubed for volume. Okay, so we just looked at the ratio of the volumes, but now we have to look at the ratio of the masses, right? Because that's part of the density. So the mass of the lead is 10,200 and the mass of the uranium is 5,094. So 10,200 over 5,094 tells us that we have a 2 to 1 ratio for mass. Okay, so this is our volume ratio circled in red, and this is our mass ratio circled in blue. Okay, so what does this tell us? Now this tells us simply that the lead is 3.375 times the size of the uranium, but only 2 times the mass. What does this tell us? Therefore, and if you don't know, this symbol means therefore, the uranium is denser. Basically because the lead is a larger size but weighs less. Okay, and so the uranium is smaller and weighs more, and their density is affected in such a way. Okay, so if you see a problem like this again, what I would tell you to do is use your knowledge of the volume ratio to find to find the volume ratio. Use your knowledge of this sort of x to y is x cubed to y cubed when we're discussing volume. And then it tells us, and then you just tells us that this is what density is, mass to volume. So you find the mass, and then you can find out which one is denser. Okay? This was a little harder, but you guys are capable.